Hello, welcome to chemistry today, the chemistry part of physical science. We are finishing up our discussion on the phases of matter, and then we're going to talk about gas laws next week, and that'll culminate our kinetic theory notes and chapter, and we should probably have a test by the end of next week. So the phase changes in matter we already saw yesterday when we were looking at our lab and our graphs that we have for our lab. The one thing I wanted to mention, because I did look at the video I made, and one thing I wanted to mention about that was when we looked at our graph, we had this situation, this, and then this, and then this. Okay, and we talked about what was happening in this area, and we were talking about the heat energy that was added to the system was used to break down the, in this piece, it was used to break down the crystalline structure of the ice. So that's why we didn't see that added temperature, because all the energy we were putting in was used to break down that structure. And then up here, we were talking about the energy that was being put into the system was being used to disrupt completely those attractive forces. So we talk about disruptive and attractive forces, and disruptive then would be forces that disrupt something. So if you're thinking of going from a solid to a liquid, and if you look at the notes, there's going to be more disruptive forces in a liquid than there are in a solid. And the attractive forces then are going to be higher in a solid than a liquid. Okay? So with that in mind, what do you think about the disruptive and attractive forces up here? What happens when we go from a liquid to a gas? Yeah, thanks, Mac. The disruptive forces then are kind of controlling the system when it's a gas. Or in a liquid, they say the disruptive and attractive forces are about equal, because we know the particles are very close together, but they're still able to move around each other. So they're attractive enough that they're stuck together, kind of, and they're disruptive enough that they can move freely. So those, disruptive and attractive forces, those aren't any like true forces, but they're a way that we talk about what's happening with molecules. Okay. Now, here we said that we had melting and freezing points, right? And then here we said we had vaporization. So I was hoping that the word would come out, but it didn't. It's actually called boiling point and condensation point, okay? Now I just want you to know that vaporization can be two different types. Vaporization, and we'll further talk about that in the notes, but vaporization is just turning from a liquid to a gas. So that can be boiling, but it also can happen when we evaporate. Which evaporation is a different process. That's when something turns from a gas to a liquid without heat added. So I'm going to explain this here. Here's the top of the surface, and if we looked real close at the top of the surface, we would see these particles of water, and they'd be moving around. And you know the molecule of water is like this, right? And when we're in ice, then we're going to have a regular pattern of these molecules. And then this is going to be like, there's a bond we talked about yesterday between the hydrogen and oxygen, like it's a partial bond. It's not a chemical bond, but there's an attraction. And we'll talk about later that the hydrogen has a partial positive bond, negative has partial negative, and then oxygen has partial negative. And just like magnets, and they're attracted to each other. And that energy is what breaks that up when we go from from a solid to a liquid. So these circles here are really molecules of H2O, but instead of just drawing like this, I'm going to say that these are the water molecules here. Now, if I look at this, if I take this molecule here, it might be down here later, and then one that's down here might be over there. These things are moving around each other, but they're staying close together in a liquid. But the difference between boiling and evaporation is evaporation only happens at the surface of the liquid. And the reason why evaporation happens is because, like, let's say I have a piece of nitrogen up here, which is N2, right? And it's floating around. Now, I notice, does this nitrogen actually collide with the water molecule? Okay, we have to use the word collide as, my hands are colliding. So if you hit something and bounce off, it's called a collision. Now I know we maybe had a misconception on the collision part pieces because we said nothing actually touches, but collisions still occur. It's just they don't actually physically touch. So, like, my hands are colliding. So part of this kinetic theory is there is collisions happening all the time. So we need to use that word correctly. Okay, but they don't touch, but they do collide. Okay. Okay, check the links on Moodle. So nitrogen here might be hitting this particle, but maybe another nitrogen comes in from another piece, and maybe kind of like a really fast one, because these nitrogens would all have individual different velocities, because they're hitting each other, they're colliding constantly, like the pool balls on a table. They're not always going the same speed. Here's another thing that we have to talk about. When we say temperature, you have to know that it is directly related to velocity. Or if I say velocity, which is another kind of term for speed, but it has direction, you have to know I'm talking temperature. So if I have a higher temperature, the particles are actually moving faster. But temperature is directly related to average kinetic energy per particle. So that means this one might, if these are all nitrogens, this one might be zooming in at 900 meters per second, when this one's zooming in at maybe 150 meters per second. So the temperature is an average of all these kinetic energies and speeds, put together and then divided by all the numbers of the particles. So what happens with evaporation is, let's say this piece gets hit by all three of these pieces, and all those energies then are absorbed by this at the same amount of time, or at the same time, and then all of a sudden this starts moving so fast, it takes off, and it becomes a piece of gas. That's what evaporation is, okay? So evaporation is a vaporization, but it only happens kind of by chance because of the collisions that are happening from the fluid above the surface of the more dense fluid. Okay, so back to the notes. So phase change doesn't matter. Adding or removing kinetic energy by raising or lowering the temperature at of a material is the cause of a phase change. So when you add or remove kinetic energy, now another thing I wanted to talk about was your understanding of the word thermal energy. Okay, so thermal energy is the summation of all kinetic energies in a substance. So that means you add up all the little tiny kinetic energies and you have thermal energy. The other word that we've been using for thermal energy is, rhymes with meat? Heat. Okay, so thermal energy or heat, and kind of the chemistry definition of heat is this thermal energy. Physics definition of heat can kind of be how much energy is transferred. It's really the same thing. Okay, so when we're melting something, the melting point of a solid is when it gains enough kinetic energy, or if you think of all the kinetic energy added up, thermal energy, to balance the attractive forces and allow the particles to flow over each other. So in other words, now there's disruptive forces coming into play. Where in a solid, it's just attractive forces, and then wiggling and jiggling. In a liquid, then, it's kind of a balance of the attractive and disruptive forces. And so the particles are free to move around, but they're still just as close, or fairly as close to each other, almost as close to each other as they are in the solid. Okay, a sucker can melt in your mouth, right? If something has a lower melting point, that means that the attractive forces of that solid are weaker. So, for example, does air have, at room temperature, does air have a lower melting point than aluminum foil? Well, the question was, through your observations of aluminum foil and air at room temperature, which has a lower melting point? Well, you can observe air in the gas form at room temperature, which means it's already past the melting stage, right? Aluminum foil, though, is frozen. Do you agree with that? Do things have to be cold to be frozen? No, because all this stuff you see in solid form is frozen. And if you heat it up enough, it might melt, or depending on what it is, it might just burst into flames. It might just change chemically before it melts, depending on what is around. Okay, so lead has a melting point of 327. An oven burner has a melting point of 500.
Wait, you can burn an oven?
Well, it's made out of metal. So any metal you can melt, right? Some liquids boil from the heat of your hand. I have one of those here if you'd like to look at it. Okay, so you asked about mercury melting at room temperature. If you go to this periodic table, ptable.com, you can see it there. This is an interactive periodic table, so it's pretty cool. But if I click on mercury there, it'll tell me a lot of information about it. But this is what it looks like there at room temperature. See how it's liquid right here? And does it give melting points and things like that? It certainly does. It gives a lot of things. But the melting point you can see here is negative 38.8 Celsius. So that's much cooler than room temperature. So I said the notes say that it melts at room temperature. The notes say that it melts at room temperature here, but it's already melted at room temperature. Okay. Okay. Yeah, it depends on if you're looking Celsius or Fahrenheit or whatever. Okay, so some liquids boil from the heat of your hand. Now, what I showed you there wasn't a boiling, but I will show you what actually happens, and that would be this. So you have the bulb here, right? And I guess the secret of this is it's contained. It's not open to the atmosphere. And then we have another bulb here, and then we have this tube that comes down here into the liquid, but it's open. So here's your liquid. So what happens is when you grasp this thing, and you had an alien hand that day, the particles in your hand are moving, right? And those particles hit the glass, which makes the glass move more. And the glass is touching the liquid, which makes the liquid move more. And we get this heat added. What happens to particles or usually when substances get warmer, what happens to them? They get faster and they need more room, spread apart. So there's thermal expansion, it's called. right here, and this liquid. Well, another thing that's happening in here is a gas, and that gas is getting hit on by these particles more, and so they're also exerting more force. So what else is happening is you're touching the gas and you're warming the gas up. And the gas starts moving faster. And then like yesterday we talked about the force of gas. We called it pressure, remember that? And if those particles are moving faster, they push on the surface of this liquid, and then the liquid moves up. Because in the end, all the liquid is gone here because this gas has put on so much pressure onto the liquid that it's boiling. Well, it looks like it's boiling. That wasn't actually boiling. Okay. Does that answer your question about why that happened? Or do you... Okay, so now we have evaporation. And we did a good job talking about the evaporation. And that evaporation could be caused from the gas particles outside, like I showed in the picture, but it could also be caused from one piece of liquid getting hit by like 5 or 6 different particles in the liquid and getting squished out too. So that, or it could be a combination of the gas and liquid hitting, kind of ganging up on one piece, giving it a lot of energy. Just like at a pool table, you see some balls all of a sudden just jump out at you on a break. Well, it's because they've been hit by a bunch of different balls kind of in the right way, where they absorb all that energy. Okay, so when something evaporates, it's called a cooling process, because the most energetic part of the liquid then leaves, leaving the rest of the liquid with a less average temperature. And actually, in reality, you would almost think that boiling is also a cooling process to the liquid, which seems counterintuitive, but the most energetic particles leave in gas form. Okay? And we did talk about this, the energy that causes evaporation could be by the distribution of speeds, by the air, which would be the warmer surroundings, and then sunlight striking the surface of the liquid. Because sunlight is radiation. We'll talk about that later. And that can be absorbed. Any questions about that? Okay, so boiling, bubbles form, changes from a liquid to a gas. We talked about that pretty good yesterday. We did have notes on that yesterday, which is actually on the video from yesterday. And we talked about the time that the pressure of the gas particles inside the liquid equals the air pressure is when something will boil. Okay? Boiling point is affected by 2 forces. The attraction of the particles must be completely overcome. And then pressure. So we'll talk about pressure a lot more in the next part of this chapter, but if, and what this is trying to explain about pressure is if this is going to expand and boil at 100 degrees Celsius, it's because it's matching the air pressure above, right? But if somehow I can increase my air pressure and make it bigger, then this has to match that same pressure to come out a solution. So if I increase my pressure on the surface of the liquid, then my boiling point is going to be bigger than 100 degrees Celsius. If I'm able to, and maybe next week I'll be able to show you this, if I'm able to make my air pressure less, then there'll be less pressure that needs to occur here, and my boiling point would be less than 100 degrees Celsius. I'll maybe try to show you that. We've been able to boil things down to 22 degrees Celsius in my chemistry class a few years ago. Or boil water, not things. Water, so if we can get it to go in here, that'll be fun. Okay. So, boiling point, the attraction must be completely overcome. As the pressure on top of the fluid becomes bigger, we will need more kinetic energy to overcome that pressure. Okay, so that's what a pressure cooker is all about. Okay, so condensation then is the opposite of boiling, and it's when things go from a gas down into a liquid. Okay. So condensation, phase changes also occurs when kinetic energy is removed from particles by lowering the temp. Okay, so I'm going to ask a question. Particles and matter are in motion all the time unless their temperature is 0 Kelvin.
That is true.
Well, that's what we think is true. So we would have to put true for that because Kelvin is temperature, and temperature is related to the motion of the particles. So if there's 0 temperature, there's 0 motion, which some people say things cease to exist at that point or become black holes. Particles never collide with one another. Well, I know that's false right away because they're always colliding. That's what this whole kinetic theory is about. When diffusion is done, the particles in the matter are equal. We spread out, right? So another word for that would be equilibrium. The amount of energy required for a liquid at its boiling point to become a gas is the heat of vaporization. Most solids are, well, they're, what? Most solids are, matter that has a definite shape, that's easy. Matter that takes the shape of its container and is highly compressible? Gas. What if it takes the shape of the bottom of the container? What is it?
Liquid.
Liquid, because it doesn't escape its own boundaries. Matter in which the attractive and destructive forces are equal about? Liquid. What state of matter is able to spread out evenly in all directions to take the shape of the container? Gas. At room temperature, which of the following are the attractive forces greater than the opposing forces of the substance? Aluminum foil, nitrogen, water, or none of the above? What do you think? Aluminum foil, because that'd be all solids, because water, they're about the same. The amount of energy to change a material from liquid to a gas is called vaporization. As the sample matter is heated, its particles move faster. They collide, they move faster, they collide more often. The idea that matter is made up of small particles in constant motion is kinetic theory. Very good. The total energy of all the particles in the substance is its heat or thermal energy. Better memorize that. The average speed or kinetic energy of the particles in the substance is its temperature. Is its temperature. Fluid's resistance to flow is viscosity. Particles that make up a solid move faster or slower than a gas? Slower than a gas. Where can plasma be found?
In the stars.
In the stars, in the
Fluorescent light bulbs.
gas torch, in the fluorescent light bulbs. Okay, hopefully you guys study this stuff and are ready for the retest on Monday. Have a good weekend. Are you ready to